So, in continuing our study of the Turing degrees, we have actually asked this question a couple of times. So we call it degree A a minimal degree if A is non-zero and for every D which is less than A, we have that D is equal to 0. That's exactly the definition. Oh, or equivalently, there is no degree strictly between 0 and A, right? This says exactly that if you look at the question of Turing degrees, down here is 0, here is this degree A. Look at the cone below it, right? This bit here is empty, there's nothing in there. So this is a minimal degree. We've also had a bunch of times that no minimal T degree exists, even though we haven't given any proof of this, but that's coming. But we've never answered the question, do minimal degrees exist at all? And that'll be the goal for the remainder of today. Try and at least get most of the way through showing that yes, minimal degrees exist. I don't really care about the complexity of them, but it turns out that yes, minimal degrees exist, and the questions we have to ask in the constructions are zero double jump questions. So minimal degrees exist below zero double jump. Okay. So, first we have a little bit of a mess of notation and definitions to work through, but they are the right way to present the proof. So bear with me for a moment. So beta and gamma split alpha if, well, alpha is initial segment of both of them and they're incompatible. Nothing special. Here is alpha and then there go beta and gamma, right? They split them in exactly the picture explains what happens. We have the notion of a function tree. So, and the notion of a function tree isn't much more than a real tree, but it's an ordinary everyday tree, except that it's one with a level of bookkeeping on top of it. What is a function tree? It is a function from 2 to the less than omega to 2 to the less than omega, which is partial computable. The ones we care about, or the ones we'll use most, are in fact total computable. So the domain is a full binary tree, and the range is, well, to every node in this tree you associate another node. Well, we allow partiality, so we want to say when is what defined. Well, if one of T alpha followed by 0 or T alpha followed by 1 is defined, then all are defined and T alpha not T alpha 1 split T alpha. So what this is saying is, right, here you have in the domain alpha which splits, right, 0, 1, there's the alpha. Then in the range, well, T alpha is an arbitrary finite sequence, so it can be pretty, in particular, it can be a lot longer than alpha. It can't be shorter than alpha, because every time you split in the domain side, you also split in the range side. So you need to become at least one longer, but you can become a lot longer. And then you split, and again, here it splits in just one extra step. Here it can be a lot longer, a lot further split. So, what is this kind of function tree? Well, this function tree is just an ordinary tree, but where you have kept track of exactly all the locations where you split.
Your image could split more than your domain tree.
Pardon?
Couldn't your image split more? Just like less?
My domain is the full binary tree. I'm not sure how you can split more than the full binary tree.
No.
And with that, all I
T,
need to say
let's
is I
say
don't understand.
your domain, right? So your domain's, I thought you said it was partial, right? So.
Yeah,
Oh,
but
it's possible to be partial, yes.
the conditions on what is defined and what's not prohibit you from only going off in one branch, I think. Right? If you can go in one direction, if you go on the other as well.
Sure. Yeah.
Yeah, that's exactly what it
Yeah,
says.
yeah.
If one direction is defined, then the other is
Yeah,
as well.
yeah.
Right? The domain here is a binary tree with this additional condition. I don't know.
Okay.
That splits everywhere where it's defined.
Yeah.
That's exactly what it is. But everything can stretch a lot longer, right? So if you have a total function tree, or F3 as these things also are known, if you have a total F3, then it is exactly a tree, graph theoretically isomorphic to a full binary tree, but everywhere the segments are stretched out. And then there are some obvious definitions. We say sigma is on T if sigma is one of these nodes that really appear in the range of T. That's what it means to be on T. A real A is on T if infinitely many initial segments of A are on T, right? If A is a branch through this tree. Well, a sigma on T really means that sigma is one of the images here. So sigma is not one of these things that appears in between two nodes of the trees. Being on the tree means you're really one of the nodes indicated by T. T1, a subtree of T2, or a subfunction tree of T2, means that every node that is on T2 is also on T. I pointed to T1. Every node that is on T1 is also on T2. But it doesn't mean that they are the image of the same thing in the domain. Right? It could be that here, this is the image of alpha in T2, and then this is the image of alpha in T1. Right? You split in the same way, in the same things. Everything on T1 is on T2, but you can skip certain things. Right? So you can look at this as we are very interested in all of these splittings. A subtree T1 is a sub-collection of the splittings. You leave certain splittings out, you keep certain other splittings. That is what function trees are about. Here's a notation. If nu is the image of T alpha for such a function tree, then T nu of beta is T of alpha join beta. And this is exactly the tree you expect it to be. Right? You have nu in your tree. Which trees should T nu be? Well, it should be exactly the tree up here. And exactly the tree up there is defined like this. But notice that the alpha here is in the domain, the nu is in the range. Okay, now, right, why do this definition? Well, because of the following: nu and t e split nu on t. Right, e is the index of some Turing machine. If, well, not surprisingly, they are on T and they are extensions of nu. So they are exactly like in the picture. We have some node and then we have two longer nodes. Notice that according to this, they don't have to be the direct next longer nodes. Just some longer nodes in the tree. So this happens, and now comes the interesting part. There exists an x and there exists a t such that phi e t of sigma of rho of x converges and is different than phi e t of x, which converges with tau. Right? So what this says is that nu gets E split by gamma and tau if, right, gamma and tau are extensions of the oracle as it is determined by nu, and these extensions allow you to compute a different value. Right? And this now we've seen before where we have looked for situations where we had nu already determined as an initial segment of the characteristic function of the set we were looking at, and we were trying to decide, can I extend this initial segment in such a way that this particular computation starts doing different things? And so a node is E-split on the tree if within the tree. Right? Why within the tree? Because the tree is the restrictions you've already accepted from before, that you are going to have to stick within the tree, but within the restrictions from your work before, you can find these two different extensions of the oracle which result in a different computation. We call tree T E-splitting. If whenever you look at T alpha naught, and T alpha 1, T alpha naught and T alpha 1 E-split T alpha. So I said in the definition of E-split, gamma and tau don't have to be the immediate extensions of nu, but in a tree which is E-splitting, it always is the case that the next level is splitting. Which is exactly why we wanted the next level to be longer, because in order to achieve such a splitting, you might have to define the oracle rho and tau on 1,000,000 more locations, as opposed to just one more. And the function tree has a good way of bookkeeping for these. The fact that these 1,000,000 more extra steps of these extensions are related to one splitting. And then the tree is E-splitting if it happens everywhere, so then you split here once, and then at the next place you again split, and again you define both of them in 1,000,000 more locations, but again in sufficiently many more locations so that somewhere a different value is computed.
Can I ask a question?
Absolutely.
Why even have the time restriction? If you're just saying there is some time where they could do something different.
Well, this is now computable.
It's just so it's computable.
Yeah.
But does it say the same thing if you take that quantifier?
If they converge to different values,
And they do
then
it
they
sometimes.
do it at some point in time.
Right.
So yes. But
Just so it's stated in a computable.
it's clearly sigma 1 now. And I lied a little bit, I guess, because before I said I don't really care. Oh, and I forgot it young too. I don't really care about the complexity, but in the end I will observe that it's 0 double jump. Right? And so this being a sigma 1 thing is going to go into that decision. A node new. Other questions?
So if every node on a tree has some nodes above it that e-split it, then there is a subtree that is e-splitting. Is that
Absolutely.
just making sure I'm
Absolutely. And that is in fact half of our eventual construction.
okay?
That we're given a tree. If we can find this e-splitting subtree, then we go to it. If we can't, we need to do something else. Well, it turns out if we can't, we don't really have to do anything. We already won. New on T is E black. If there are no e-splittings above mu. Right, and this is not about immediate e-splittings, no e-splittings at all. If there are no e-splittings at all, that's why the definition of e-split does not require rho and tau to be immediate extensions. But if it's E black, exactly when this strategy fails extraordinarily miserably, right? You could still have that there is a finite number of e-splittings, and then your search for e-splitting stops, and you come to a stop. But when you're E black, you will never find an e-splitting. Right? This is clearly something you can search for, and if you find it, you find it. If you don't find it, you never know you didn't find it. Right? That's why it's sigma 1. A node is called E wide if the immediate extensions e-split. A node is called E gray otherwise. Right? So the E gray nodes are just the nodes where there are some splittings above there, but they might be far away.
Is there a reason for this notation?
Well, we like things to be black or white, and gray is kind of fuzzy and unpleasant. It's just the usual thing of definitions. Definitions allow you not to say anything more than you could otherwise say, but you can say it shorter. Right? E black is shorter than there are no e-splittings above mu in the tree. That's the only a 3T is E wide or E black if all nodes are. So E black just means all nodes are E black. E white means all nodes are E white. Right? It's monochromatic. Otherwise, the 3T, surprise, surprise, is E gray. But of course, E gray doesn't mean that all nodes are E gray. It just means that there are maybe some gray nodes, but maybe some white nodes, maybe some black nodes, but certainly not all of the same color. Well, I guess all nodes could be E gray in the E gray tree, but not all white or all black. And those are the trees we like, the ones that are E white or E black, because they are the same thing keeps happening. Okay, so now I can remember the theorem we're after. The theorem we're after says there exists a minimal degree. So how do you do this? Well, in our usual style, we do this by setting up an infinite list of requirements and then observing A, that we can satisfy these requirements, and B, that these requirements are sufficient. That's not true, right? Usually it's A, see that these requirements are sufficient, and then B, see that we can satisfy them. So now after all this work, I can write down the requirements, my requirement RE, the E requirement is going to be the set A, whose degree is going to be minimal, lies on a total F3, which is E black or E white. Right? So my A, or its characteristic function, is a branch through some total E black or E white 3. And then the claim is, if I can construct such an A, and presumably while I'm constructing it, I'm figuring out what these trees are. So I'll probably construct A and the trees at the same time, or something like that. If I can make such an A and show the existence of these trees, then the degree of A is a minimal degree. Okay. What does this mean? Well, it means okay, first of all, if A, let's presume for probably the remainder of the lecture, I'm not sure if I'll get further, but let's presume that A satisfies all requirements RE, and let's start analyzing what this buys us. So according to my statement so far, this should mean the degree of A is minimal. What did minimal mean? Well, it was right here a while ago. And not computable. Anything which is there's many different ways you can formulate it, right? And I already wrote down two, I think. Anything which is strictly below it is computable, or anything which is less than or equal to it is either computable or Turing equivalent to A, or there's nothing strictly between it and the computable degree. One of these things. But certainly, requirement number one, A should not be computable. Right? So we need to see A is not computable because the degree of the computable sets we completely understand is the bottom degree. There's in our point of view, nothing of interest going on there. Okay. So what happens? A is not computable. And now we need to show that if A were computable, then one of these requirements is contradicted. Right? So assume A is computable, which isn't supposed to happen. Can we come up with a 3 No. But coming up with a tree is not the right strategy, as you noticed me getting confused by, because it lies on some trees, but it does. The requirements don't say it lies on all trees, right? So you cannot come up with a tree. But what we can come up with is a computation and show that for this particular E, for that particular computation, this A could not lie on an E white or an E black tree. Right? We need to come up with an E such that A could not lie on an E white or an E black tree. Here it is. Phi E of sigma of x. Yes, right. I'm defining what E is in this equation with the computations. Well, it is sigma x if sigma is incompatible with A, and it diverges if sigma is compatible with A. And now you need to look at this for a little bit and see if it makes sense. But if you have sigma, then computing sigma x is fairly easy, right? You just ask the oracle what to do. Starting to diverge, also perfectly fine. But these two are I hope, a little bit unsettling. Because we cannot have this computation go and determine completely what sigma is. Right? It is an oracle computation. It can ask oracle questions, but as soon as it makes the mistake of asking a question which is not in the domain of the oracle, the computation diverges. So it is not the case that phi of E knows what sigma is, then using this knowledge of sigma determines which of the two cases is the case. Yes. Right? But that's why the cases are specially formed like this, because these two cases, this case distinction, it can make. Right? How do you make this case distinction, and why is this then forced to be divergent? Right? You make this case distinction by starting asking what is sigma at 0. You get an answer back. Then you check with A whether you agree with A or not. Right? Why can you do that? Because we're working under the assumption that A is computable. So you can check, does it agree in the first place? Then you check, does it agree in the second place? Then you check, does it agree in the third place? Now, if sigma is an initial segment of A, then you keep going on, and every time you say, does it agree with A? And the answer is yes, until you make the mistake of asking an oracle question, which is outside of the range of the oracle, outside of the domain of the oracle, and you diverge, which is exactly what you want if you're an initial segment. So this method automatically gives you the right answer here, which is also why you're forced to have divergence in this case. If sigma is not an initial segment of A, then you keep asking these questions. Does 0 agree? Does 2 agree? Does 4 agree? Does 5 agree? And at some point you get, no, you do not agree. Then you know you're in the other case. But you know in the other case, effectively, at some finite time without going into divergence, you know I am in the case where they're incompatible. Therefore, ask one more oracle question. This, of course, might be undefined, but if sigma is, if x is not too long, then it is defined, and you go into that. So that's why, if A is computable, then such an E exists. Now, of course, E depends on the Turing machine that computes A, right? Because you need to check A. But if A is computable, such an E exists. So you have this. Particular computable thing. Now, according to our assumption, A lies on an E black or an E white tree for every E, in particular for this E. Right? A lies, the A we're dealing with here, lies on an E white or an E black tree, according to our assumptions. So this is going to be a contradiction, because so the tree it is on is either E white or E black. And like I said before, I have no idea what this tree looks like, other than that it is total and it is supposed to be E black or E white. This is what I know about my tree. So what did it mean? E black meant no E splittings above nu. But now look at the tree. This tree. Here is the node nu. We presume we are on an E black tree, so every node on the tree is black. In particular, this node nu on the tree is black. Black meant no splittings above nu. Remember again, it's not talking about immediate splittings, it's talking about splittings at all. But if I look at nu, some initial segment of A, and I extend here, this is the infinite branch that A lies on. So my phi E, everywhere along this branch it diverges, but it also splits in many locations. Now, let's take two of these splittings that go off. In both of these cases, maybe I should do it like this. Right, our tree is a total F tree, so above every node there is a splitting. So this last minute splitting I added here exists. And now what happens is, for each of these, sigma naught, sigma 1, and sigma 2, there exists an X where they are defined, right? At this level here. I don't know what it is, but if I use this height as an input, then I get here a 1, and a 0. And so here, because I have both a 1 and a 0 at that location, in particular, one of the two is different from the thing I had over here. So this shows that, okay, the immediate splitting that follows is not necessarily an E splitting, but if I go after the immediate splitting and then one more splitting, then I can find a location where this computation is defined and gives different values. Therefore, there is a splitting above this node nu. And if there is a splitting, then the node is not black. So this shows that the total F3 A is on is not E black. Therefore, it should be E white. What did it mean to be E white? E white meant, well, not only are there splittings above, which we just showed, but the splitting is immediate. But the splitting can't be immediate, because what did it mean for a splitting to be immediate? It means at the next node we split in two places, and there exists an input on which both are defined and give different values. But this one oracle is an initial segment of A, so it's nowhere defined there. This computation is nowhere defined. It doesn't depend on X, it's nowhere defined. So in particular, in this tree, you can have no E white nodes. And so now I've argued that this arbitrary node on the tree, well, it's not entirely arbitrary, it's an initial segment of A, right? This node, which is an initial segment of A, cannot be E black, it cannot be E white, which is a contradiction with the existence of there being a total E black or E white E tree, F tree. Right? And notice that that's the key it depends on is E black means no splittings, E white means the immediate extensions are splitting. This is right. These definitions are not necessarily subtle, but the word immediate is not accidental, right? This is the key word here. in particular this tree, right? You can certainly thin it out to become E wide, but then A is no longer a branch through that tree. That's the trick. Oh, I'll finish this on Friday. So now we want to see that it's not computable. Well, let's still leave the other requirement. The other requirement says that well, first of all, how are we going to do this? First of all, we're going to show that if something is computable from this A, yes. Anything which is computable from this A is computable by some Turing machine E, and then E wide means that this whole thing was computable, and E black meant that A can be computed from it. Now I said it exactly the wrong way around. E wide, every node is splitting, means that from this thing which you computed from A, you can determine what A was. And E black meant that, well, this thing which you computed from A, it could be computed by the same Turing machine from any branch through this tree, and the tree is computable, so you just work from the branches in the tree and it'll follow. So that'll be Friday.